to present the experiment that I did at the NEUROMED Institute in Italy during my research stay there in terms of the PETAL project. So what we did in short is that we looked at the sap velocity with two methods. First, a heat pulse sensor that I brought from Ghent University, and then the PET scanner that was available at the NEUROMED Institute. And because I think most of the audience here is familiar with PET imaging, I'm going to focus the introduction on the sap flow sensor that I used. So we print these sensors in-house with a 3D printer, and it consists of a thermistor in the center that emits a heat pulse, and a top and a bottom temperature sensor that measure the heat increase in the plant tissue. And because we are working with really tiny increments of temperature, once we wrap the sensor around a plant stem, we wrap the sensor with tube insulation to avoid getting temperature changes in the measurements from the environment when the sun comes through the cloud or something. So the thermistor sends out a heat pulse, and if there's no flow, then this pulse reaches the top and the bottom sensor at the same time and with the same temperature. So the graph would look like the graph on the left. But if there is sap flow going on in the stem, then the heat pulse is dragged along with the sap, and then the heat that is reached in the top sensor is a little bit higher than in the bottom sensor. And this allows us to calculate a certain ratio from the raw data. And this ratio is then used to calculate sap velocity. Now, in this equation, the parameter K is really important. This is the thermal diffusivity. So it expresses how fast the heat is transported in the plant tissue itself, with or without the flow present. But this thermal diffusivity is really hard to measure. We know its value in water and dry wood, and we expect for plants that this value lays in between these two values. And a few years ago, I did an experiment to calibrate the sensor, and I calculated a thermal diffusivity of 5 square centimeters per second, which is really, really high. It's 1,000 times higher than what we would expect in plants or what we measure in trees, for example. And it's even 10 times higher than what's the thermal diffusivity in air. So that was really strange, and I thought there's no way that this is correct. And while I could use this value because I calibrated it for flow, which is calculated from the sap velocity. So sap velocity was an intermediate value that I didn't really need at that point. But I thought the velocities calculated with this calibrated value were way, way too high. So that was the goal for the experiment that I did at NEUROMED, was to validate these sap flow sensors and at least this parameter value with PET imaging. Because the idea was with PET imaging, I can visualize the sap flow and just look at how fast it goes. So in order to validate it, we put wheat plants in the PET scanner available. We added additional lighting to make sure that there was enough sap flow going on. We installed 2 plants with 2 sap flow sensors per plant that had a heat pulse every 15 minutes. And then we applied, at the cut stem, we applied FDG dissolved in water. So this water would be taken up and measured in the scanner. We had 2 scans of an hour immediately next to each other, and then in total 12 repetitions. But this setup wasn't enough to have accurate data of the sap flow sensors. So before the scan, we had a pre-scanning period to help acclimatize the plants to the environment of the scanner. Because as you can see in the figure on the right, this shows the raw data of the temperature sensors. And in this figure, you see that in the pre-scanning phase, the temperature is still increasing a lot inside the scanner. because of the lights present and the scanner being turned on. And while an increasing temperature, it can give good data with the sensors, it's less reliable. So we put the plants in the scanners for an hour or a small hour. And we didn't cut the stems yet at that point. So we left the roots in this falcon tube with a moist paper towel to make sure that there was enough water flowing in the plants and they wouldn't dehydrate yet. And then the next step was to scan the plants. So in the beginning, we cut the stem just underneath a node because I was worried that the water containing the FDG would be taken up by surface tension in the hollow pith, because wheat stems, they have a hollow pith. So it was cut just underneath the node, and then we put the syringes around it and injected the FDG into the syringes. And then we scanned for 2 hours, and then after the scan was also important. I cut the plants just above and below the 2 sap flow sensors, wrapped it again in moist paper towel to avoid dehydration. And this was, it turned out really important to do this because when you cut a plant, the sap flow stops and then you can measure a 0 velocity. And it was important to normalize the sensor data with this. Then I can already go to the data of the sap flow sensors. So you see here 2 examples of 2 sensors. And in the pre-scanning phase, you see there is a lot of variation, more than what I would like. Also in between the scans, when the table bed moved out of the scanner, there was a lot of interference, and these measurements were not good. But during the periods that we scanned, I was really happy with this data. So we measured velocities of around 10 millimeter per second, which was a lot faster than I was expecting. And that also led to the bed data that was different than what I was hoping for. So I was hoping to see the progression of the first FDG signal so that I could easily calculate the velocity, but that was not the case. So I learned that the sap flows really, really fast. And right from the start of the scanning at 0 minutes, you can see on the left figure that the FDG signal was already at the top of the plant. So I had to get velocity data in a different way. And to that end, I'm using compartmental modeling. So this model is based on a model by a colleague from a few years ago. And it's performed in the phytosim modeling software. And it's based on the data from the time activity curves from regions of interest. So you draw a few regions of interest around the stem, and the bottom one, the data you get from that region of interest, so the time activity curve, it serves as an input for the model, and the time activity curves from the other regions of interest, they serve as calibration data. So what the model does is it calculates the velocity, but it not only accounts for water, or in this case, at FDG flowing through the xylem upwards, but it also allows water or FDG being stored in each region of interest, or even a loss of signal due to, for example, transpiration. So all these different velocities, they can be calculated with the model, but I'm interested in the velocity, of course, in the upwards velocity. So the analysis looks a bit like this. After drawing the ROIs and with the time activity curves, the data you can see are the dots on the figures. And then the model tries to fit the different velocities to the data, and you can see the simulation in as a straight line. And so the result of this simulation, this example, is 5.6 millimeter per second. And then as an overview, I have only preliminary results because I haven't gone through all the data yet. But you can see that the first results of the PET data shows velocities of around 5 millimeters per second, while those same plants show around 10 millimeters per second, so about double the velocity. But I'm actually really glad with this result, because I thought with a thermal diffusivity of 1,000 times too big, I was expecting velocities to be also 1,000 times too big, but that's not the case. So the conclusion is that this parameter, the order of magnitude, is correct, surprisingly. And I hypothesize that it has something to do with the air pockets being trapped in the hollow pith. So this is a cross section of a wheat stem with a leaf wrapped around the stem. And so you can see a lot of air trapped in the pith, but also between the leaf and the stem. And yeah, maybe it has something to do with that, but more thinking and research is needed. So I thank you for this quick presentation. And I also want to thank the people at NEUROMED for their technological assistance and my colleagues that joined me during the research stay there.
Yeah, so hi everybody. I will present in 5 minutes all what we so our digital imaging multimodal platform in NeuroMed, where Sarah has been, and I hope will come back to continue more experiments with us. So I'm glad to see not only the results, okay, that one we always share, but also that, you know, she was okay with us. So in particular, I will focus on the available technologies for plant imaging. We don't do only plant imaging, but of course today I will show only the plant imaging part. So our focus is in positron emission tomography. So we develop mainly, so we have mainly positron emission tomography based devices. What we have and what Sarah was using for her research is a high resolution, fully digital positron emission tomography scanner. Here you see the scanner and also the related publication of it. The scanner is very specific because we did it. So it's me and my group. So that has been built by us, and this is also a specific one. Soon you will have available at our node the AgriPet. So it's a portable pet system. That one we also did in order, very compact, shape adaptive, portable, also for in-field scenarios. So what is going to happen in our node is that soon we're going to have the transition from lab-based to in-field based pet imaging. Sarah, while Sarah was with us, she saw the prototype we were testing. Sarah, you see now how it will look like. It's we have also micro MRI, so a 7 Tesla MRI, and there also we have image processing algorithm for plant imaging in case, in addition to positron emission tomography, users like to do advanced MRI. Of course, the PET system has also micro CT, so we have the micro CT imaging there. I go through some images, yeah. So that is, for instance, CT imaging of, this was one user studying saline stress in zucchini, and this was CT imaging of the zucchini sprout. You see the water content inside coming from CT. That is the sort of resolution you can get out of our micro CT imaging. And of course, for PET, Sarah has already shown her nice results even with the nodes, yeah, in the width. But yeah, so what we are now doing is to have the transition from in-lab to in-field PET imaging, and so this was done in fact by us. So to test that with wheat sprouts and maizen sprouts. On the left are in-lab, there is in-lab imaging. On the right you have already examples of in-field imaging. So all that is taken in-field already with the new prototype. That is going to be, I hope, as a pilot technology available soon in our node. We have so to grow plants, we have a growth chamber with thermal and illumination stability and control with cycles. We have an hydroponic system in case users like to do hydroponic growth. We have an open field and soon also an in-field greenhouse. So a key point, that one, we didn't think that it was so good until Sarah told us that. The imaging facility and the plant grown facility are in the same building. So it means that you don't have to go to the Uniclinicum to make a PET scan to the plant, but you just go next door. And this is, of course, for a plant experiment, very important. Yeah, so this is how we built the facility, and so it came. Users give us always a positive feedback. As services, of course, I go faster here. We have the also the image analysis and processing. It was not the case of Sarah. Sarah was a very good user, as she can do also the analysis of the PET images, but often it happens to us that users cannot analyze the images or the data themselves. So we have also an image processing and analysis service, yeah, with the algorithms that we developed in order to extract quantitative parameters as velocity, diffusion coefficient, exchange rates from the different plants. As for you, we are very well, the node has got to quite a good level with European funding. So we have the PETAL project, is the project PET for agriculture and life. This was our seed funding, and on top of that now there is the AgriPET MRI project to build a new in-field PET MRI system. And we are applying to a doctoral network also through Euro-BioImaging, so and to other initiatives always related to plant imaging. So the node and the node staff is also very active in that. So, and with that, I thank you and I welcome all of you in our node.